Alright, imagine we want to build a machine learning model whose only job is to tell cats apart from dogs. It's a pretty classic problem where we take an image, convert it into some vector of features, and these could be things like, does the animal have whiskers or not, or where does the animal lie in a range of playfulness versus, I don't know, wanting to just lounge around. Essentially, what we're trying to do is approximate this function f of x, which takes in this input vector x and gives out a y, which is a prediction between a cat or a dog. Say we have 100 data points. These are our input vectors mapped to a correct label which we know to be true. Intuitively, we'd like to split this dataset into a train set and a test set. Now the model doesn't magically know how to classify cats and dogs, and we have to teach it, and it has to learn using the training set, which looks something like this. By feeding this into the model, you are giving it the direct correspondence between the input vectors and the correct output that it should be giving. So perhaps x1 has the feature of does the animal have whiskers or not set to true, and maybe in x2 that feature is set to false, so it should be more confident in answering that it's a dog. So we are supplying our model with an input vector and also telling it what the correct output should be. During training, the algorithm automatically adjusts the model's internal parameters, things like the weights in the neural networks, and at the end of it, we're inching closer to this function f of x, which we initially wanted to approximate. But once training is finished, did the model actually learn something useful? Maybe it just memorized the training images. We don't really know. So to check that, what we do is use the test set, which is usually a small subset of our entire data set. We let the model predict if it's a cat or a dog based on only an input set that it has never seen before. And it's given us an output which we can compare with the true y label that we have, because it is, of course, from our original data set with labels that we know to be true. And based on that, we can get an error score, which when we minimize, we hope that the model quality also increases and it generalizes to real world data. So here's a question that tends to confuse people. Why do we need a validation set when train and test seem to get the job done? It feels almost redundant because we already trained the model and we also have a test set to measure performance. Why introduce a third data set? The reason is that building models involves a lot of choices beyond just finding the right parameters during training. For example, suppose we're training a neural network. We might have to decide things like how many layers the network should have, or what learning rate it should use, how strong the regularization should be, or how long you want to train the model. Things like these are called hyperparameters. And these are the reason why we need the validation set. And unlike the weights of the network, these things are not learned automatically. In practice, what happens is that the developer, or when you are training the model, you try many different models with varying combination of these hyperparameters. So now an obvious question arises. If the model can learn the weights and biases on its own, how do we optimize for an ideal combo of these hyperparameters when the model itself has no influence on them? They're chosen by the developer, so you can't really let it run by itself and pick out the best set of these hyperparameters. The obvious idea is to just evaluate them on the test set and pick one with the highest accuracy. But this is where things get tricky. A helpful way to think about this is with an exam analogy. Imagine you're preparing for a final exam. Your study material is like your train set or training set, and your mock exams or your practice tests are like your validation set. So in the training set, that's where you actually learn the concepts. Now you don't know how your mind is learning this stuff, But after going through the lecture slides, you just know that you will do better on the exam. You can think of this as the model automatically adjusting the parameters, but the equivalent of that inside your mind. The validation set acts like your practice tests and mock exams. Similar to how a developer tries out hyperparameters to find out the best combination, you try out different study strategies and see which one helps you the most for the process of studying itself. That is the key insight. Suppose you use the test data set and use that error to make your model better. Essentially, you're figuring out the best strategy by giving the final exam and then looking at your scores on your final exam. Ideally, you should be doing all the dirty work of experimentation and figuring out the best method to study before you give the final exam, which is by taking the practice tests. Or else your preparation just becomes tailored to that exact exam. You have now overfit to that specific final exam, or here that acts as the test set. So in machine learning, we treat the test set to be almost like a sacred benchmark, and we want to try very hard not to touch it while developing the model. Instead, we create a validation set, which is basically a pretend test set that we're allowed to experiment with. To really drive down the concept, imagine you tried a bunch of different models. Say we have model A, B, and C, and they all have the same true accuracy. However, when you test it on the test set, say model A gives you 80%, model B gives you 96%, and model C 92%, you would intuitively pick model B to be your winner. However, this in statistics is called the winner's curse. You didn't cheat intentionally anywhere, but by repeatedly evaluating models on the test set, you've effectively started tuning your model to that specific test dataset. Again, you're overfitting to the test set now. So, at the end of it, the train set is where the model learns parameters automatically, and the validation set is where you fine-tune hyperparameters and try out different models itself and then run it again on the training set. And out of this entire process of back and forth, you send out your best model to face the final test set, and that will give you a metric of how well your model is doing. You don't want to optimize for the model by running it on the test set, and that is the key insight. So now you have validation set and the training set and the test set. What do you do with this? How do you optimize for a better model? During training, we monitor two things: the training loss and the validation loss. Here in green, we have the train loss, and this is our validation loss. On our x-axis, we have the number of epochs, or the number of training runs, where each time we are going over the entire data set. And on the y-axis, we have our loss. Training loss measures how well the model fits the data it is directly learning from. So as training continues, that number almost always keeps going down. The model is literally optimizing to reduce error on the data set. But the validation set is different. Those examples were never used to update the model's parameters. So validation loss gives us a window into how well the model is doing on unseen data, with unseen being the keyword here. Early in training, in these parts, both losses are typically decreasing. And that's a good sign because the model is learning real patterns that generalize beyond just the training set. But after some point, something happens. The training loss continues to decrease, whereas the validation loss is suddenly increasing now. The model starts fitting very specific quirks and noise in the training data beyond this point. Details that don't exist in the broader data distribution, and noises and biases are getting carried in to how the model is learning. And so the training loss continues to go down, but the model is getting better and better at fitting those specific training examples. The validation loss, however, starts to increase because those extra adjustments that the model is making do not help with unseen data. So the moment validation loss stops decreasing and begins to rise is a strong signal that the model has started overfitting. That's when we often stop training near the minimum of the validation curve, and it's the point where the model generalizes best to unseen pictures of cats and dogs, which was ultimately our initial goal.